So hi, I'm Noa, and I'm going to start to talk about statistics. So, here we go. Out of 100 people in the world, and this is not a very representative audience for 100 people around the world, about 5% of the adults would have been diagnosed with coronary heart disease, 3% will have a stroke, 10% of the whole population, once over 65, will suffer from Alzheimer's disease, and 5% of the whole population suffer from depression. But 50% of the entire population will suffer from a specific organ failure in the middle of their life. A specific organ will stop secreting its vital hormones in the middle of the life, and that vital hormone, once it's gone, that will impact every system inside our body. Now, as you probably saw, I'm talking about the ovaries, and I'm going to present myself. My name is Noa Lavi-Shoseyov. I'm a doctor in the IVF clinic in the Kaplan Hospital, and I'm also a PhD student under the mentorship of Nava Dekel and Michal Neeman here in Weizmann Institute. And I'm researching this interesting organ. This organ harbors the female gonads. A lot of us have it, and those of us, a few of us who don't have it, probably know at least one person who does. It might be one of our parents, one of our children, someone you live with or someone you work with, but let's say that everybody here either has an ovary or two, or knows someone who has one or two. So these organs, this ovary has follicles that contain an oocyte. The oocyte is the cell that eventually will produce life, will produce a baby. And these oocytes are produced very early on during gestation. It is around week 20 of gestation in humans. They are encapsulated in a small one layer of supporting somatic cells that maintain it dormant until activation. Now, they can maintain dormant for a day, and they can maintain dormant for decades, and once activated, they start growing. And they are activated before we are born. They are activated when we are babies, in childhood, but only during adolescence, when we hit puberty, a specific signal that comes from the brain and onto the ovaries help these follicles grow even more and ovulate, producing a mature oocyte that one can fertilize and have a baby. Now, when we're talking about 20 weeks of gestation, we're talking 6 million follicles, dormant follicles. By birth, we lost a lot, and we're born with about 1 million. In puberty, we're talking about 300,000. And by menopause, we are left with 1,000 follicles that will never be activated. Now, what is interesting is that from all of these millions, only 500 are going to ovulate. And what is even more fascinating is that only 5,000 are being activated. Now, I'm not into math, I'm not a mathematician, but the gap between 1 million and 5,000 that are activated is a really big gap. And that got me questioning, what is happening to all those follicles, all those dormant follicles? Now, I was asked quite a few times, okay, you're talking about follicles and ovaries, and you spoke before that about vital hormone, the menopause, right? The cessation of the ovarian function. So actually, once puberty is happening, when we get that signal from the brain and onto the ovaries, those growing follicles are the ones who are the factory that produces estrogen. That is the hormone that is so fundamental for most of the systems in our bodies. And once we are left with no follicles, once we don't have any more of this factory that produces estrogen, all sorts of bad things happen in our bodies. And it could be brain fog and hot flashes and dryness of the skin. But some of them have major health impacts, such as cardiovascular disease, bone loss, osteoporosis, dementia. And as a physician, we think it's very simple. Okay, she doesn't have estrogen, let's give her. We have pills, we have patches, we have shots, we have gels and creams. But reality, thank you, is not as simple. When a patient is in my clinic, for a lot of them, I am not allowed, I cannot prescribe them external hormones. Not only that, a lot of my patients don't want hormones, and that is okay because they also had side effects. But also, we have some of the women who suffer from early menopause, from premature ovarian insufficiency. And those women are particularly in danger of all of the side effects and all of the health risks I just mentioned. And what if I could elongate the ovarian lifespan? Because we know today that every year menopause is delayed, all the health risks I just mentioned are decreased. So, we know that we have these follicles and they are activated. We know that not all activated follicles will ovulate, some of them die in the process. But what happens to the rest of the follicles? Like the big gap that I told you about, not all of them are activated, but what happens to the rest? And that is my question. That is why I came here to answer. How can I impact the unused ovarian reserve? So in 2017, our lab published a great paper that introduced for the first time vasorin, which is a protein that was mostly investigated in vascular system. Vasorin, it makes sense. And they highlighted its activity in the ovarian physiology. They've shown that vasorin is expressed in ovarian follicles. And not only that following the LH surge, which is a signal that comes from the brain and onto the ovaries, and after that causes ovulation and triggers ovulation. Also, it upregulates the vasorin, meaning the LH prior to ovulation upregulates this vasorin. So they made a conditional knockout, a transgenic mouse, where this vasorin was specifically knocked out from growing follicles, the ones who are about to ovulate. And they found a lot of interesting things about those growing follicles. But what they also found, and I found most intriguing, is that the number of primordial follicles were half. And I want to emphasize this one because the genetic alteration did not happen in the primordial dormant follicles, only in the growing follicles. So how were they cut in half? Why were they so low in that transgenic mice? So we hypothesized that this vasorin, that is expressed by the growing follicle, either inhibits the death or the activation of these primordial follicles, and that way it helps to maintain the ovarian reserve. So vasorin, we looked at different age. We looked at prepubertal, 15-day-old, and also I looked at the 7-month-old and 18 months old that are aged mice. And we saw that this effect is maintained in all age groups, but also we didn't find a similar effect in the activated follicle, the small activated follicles that are not yet responding to the signal from the brain. They were not altered. So we understood from that through a process of some sort of interfollicular signaling pathway, these growing follicles inhibit primordial follicles' death by secreting vasorin. And that way it maintains the ovarian reserve. So we understood that not only do they die after activation, they probably die before even being activated. And the remaining question is, how? So by now we did find a signal for some of the follicles, for a small cohort of follicles inside the ovary. This is a mice ovary. The red is primordial follicles that are positive for a signal called cleaved Cas3, which is a signal for apoptosis, one of the many regulated cell death that we know of. And the blue arrows are the primordial follicles who don't have that signal. Now we found that in a very small number of follicles inside the ovaries, and they were always cohorted together, they were always clustered together. So we understand from that these follicles got some sort of external signal, maybe telling them to die. So if I will summary, my whole presentation, there is a continuous depletion in primordial follicles throughout life. The ovarian function and the follicle numbers are central to determining menopause timing. Vosorine participates in the maintenance of primordial follicles, but it does not alter the number of activated follicles, though it does increase the number of primordial follicles, probably through regulated cell death. I hope that my study will help us maybe elongate the ovarian lifespan and even delay menopause. I want to thank both of my PIs, Nava Decker and Michal Neeman, for allowing me to do this amazing research and helping me be here. I want to thank my lab members. I want to thank my IVF family. And I want to thank all the other participants of today's